So the process of producing the dual of a linear program is just a mechanical process. There's a series of steps that you go through where each constraint from the primal becomes a variable in the dual, and each variable in the primal becomes a constraint in the dual, and certain maxes become mins, and bounds become objective function things. So what I've done here is I've actually gone through that process, which we could go through in detail, but let's just pretend that we did, and we create a new linear program from the old linear program, and the new one is called the dual. So let's take a look at this dual in detail, because it turns out that the variables and the constraints actually have some very nice interpretations that are worth thinking about. Here in the dual, the thing that we're trying to optimize is we're trying to maximize the sum over all state action pairs of the reward for that state action pair times this value QSA, little QSA. So little QSA, probably not a great name for it because it's not the same as a Q value, but it's something. It's something that we're multiplying by the rewards, and we're trying to maximize it. So one way I like to think about QSA is as policy flow, sort of how much agentness is flowing through each state action pair. If it follows the policy, it's going to spend some time running around in the environment, passing through each state action pair. And each time it passes through a state action pair, we're going to get the reward associated with that state action pair. And what we want to do is maximize that reward. So from this sort of policy flow concept, it sort of makes sense what it is we're trying to maximize. It's in some ways even more intuitive than in the primal, which we were saying we're trying to minimize the value, which of course we're not really trying to minimize the value. We're just trying to minimize it so that it doesn't end up being an upper bound on the value. Here we're actually trying to maximize expected reward, which seems like a really good thing.
Right.
Okay, so this is now going to be subject to the following idea that for each state, in this case it's easier to think of them as next states. For each possible next state, we want it to be true that the amount of policy flow through that next state, summed up over all the actions that are going through it, that should be equal to, in some sense, the number of times that next state is visited, which we can get by summing over all states we might have started at and actions we might have taken from there, the policy flow through that state action pair, times the transition probability that would send us to S prime as a result of that. And we're going to also include in this equation sort of the sense that we can also start at a given state action pair. So we're just going to stick a 1 in for that. So there's some policy flow that we're injecting into each state action pair of the system. And we're going to add to that any policy flow that would be coming through it through other parts of the system. So it's kind of like we're dumping policy flow all over our MDP and then letting the MDP kind of pump around what's left. And it's discounted. There's a little discount here. So there's actually, evaporation or something happening all over the place. And what we want to know is what's the way of letting the flow go through, of kind of deciding at each state which action it should flow through so that we ultimately get the maximum possible reward.
Mm-hmm.
And I think just one additional constraint here just to make sure that the policy flow is non-negative so that we can't introduce a whole lot of policy flow in one place and then drain it out some other place to make things balance.
Right.
You can think of these constraints as actually being a kind of conservation of flow, right? So the amount of stuff going into S prime, it has to equal the amount of stuff coming out of it. And that's all this is saying, right? It's just saying that has to balance. It has to be a meaningful flow. Subject to that constraint, maximize reward. So again, this is kind of a neat interpretation of what it means to solve a Markov decision process, but it just comes mechanically out of the primal version of setting up this as a linear program.
Okay. Does that suggest an algorithm that's different from the sort of algorithms we've been using so far?
Interesting thought. So, well, for one thing, it is an algorithm, right? In the sense that once we've set things up this way, we can hit it over the head with a linear programming stick and a solution will come out.
Sure.
And in fact, it'll come out in polynomial time, which is nice.
Mm-hmm.
But you're right. I mean, in some sense, if you think about value iteration as something that's propagating these values around, this has a different form. This is really concentrating more on the policy aspect of the MDP. And maybe we could make an algorithm that more directly kind of searched in policy space for the best behavior for the MDP.
Let's do that.